Okay, welcome back to the May 2025 exams TZ2 IB Chemistry walkthrough for paper 1A HL. This video will be going over questions number 26 through 30. And so starting with question number 26 is we have this question that's asking about which species is an intermediate in this reaction mechanism. And we have a step 1 and a step 2. So in terms of this, we just have to know what an intermediate is in the first place. An intermediate is going to be something that is in the products of one step and then goes on to the reactants of the next step or a future step, if you will. It also has to cancel out and not be in the overall equation. So immediately I'm kind of looking at what is in here and then here that's in common. And so that lands me upon this cation. And so I see, okay, cool. Then just to make sure it's an intermediate, I'm just going to make sure that it is not in either of these reactants or products here, and it's not. So that tracks for being the intermediate as A. Another way that you can think about this without even looking at step 1 or step 2 is immediately you should kind of recognize this as an organic type of reaction. Okay, a substitution reaction. And so this is going to be, because it is a two-step type of reaction, it's going to be an SN1 mechanism. And so whenever you're thinking SN1 mechanism, the intermediate is the cation. So immediately, without even looking at the steps, whatever, cation, so A. That makes sense. So you can think of this either of those two ways, but you would get the right answer either way. Moving on to question number 27 is we have what is the overall reaction order? And so that's one where you literally just have to look at the data. If the concentration doubles, rate doubles, first order reactant. Concentration doubles, reaction rate doesn't change, zero order. Doubles concentration, and then it quadruples the rate, that would be second order. And then our overall is just the individual for each reactant added up together. Okay. So that's the trick, is they probably want you to just think of one reaction, but you need to consider all of them because it is the overall. Okay. So for NO, we can see that from trial, I'm going to call this T1, trial 2, trial 3, because it's not labeled. So I'm going to say that in this going from trial 1 to trial 3 is you have your concentration of NO doubling and your concentration of Cl2 remains the same. So that's good. You want it to be the same just to see the effect of the NO. And so whenever you look at the rate, is that then quadruples. Okay, it's 2.5 to 10. So that is times 4. So that is going to be times 4. So the concentration of NO is going to be second order. For Cl2, you can see that from trial 1 to trial 2, you are doubling the concentration of Cl2. Your NO remains the same, and then your rate also doubles. So the reaction is going to be first order with regards to Cl2. Okay, and so then for the overall order, 2 plus 1 equals, you guessed it, 3. I sure hope you know how to do that math equation. So in this case, the answer will be D. That it is third order overall. Okay, so that will be number 27. Now on to question number 28. We have what is true of rate constants of elementary reactions. Okay, full disclosure here. When I took this exam myself, this one got me. Why? I'll explain. So immediately you're like, okay, rate constant, temperature. It's basically what this is asking about because all of the options have temperature in it. Okay, and so I'm thinking, okay, let me look at that Arrhenius equation. Okay, and so I go over to my data booklet because I don't have it memorized. I don't have to memorize things because I'm a teacher. Anyways, so I see that Arrhenius equation. K is AE raised to negative EA over RT. Okay, and so I'm going to write that down over here. K is equal to AE negative EA over RT. And so my dumb little brain saw the little options of always and then endothermic and exothermic. Endothermic and exothermic are there as distractors. Boy, were they distracting. My thought was, oh, so that would be the active, that'd be the EA. For some reason, myself, and this is what they wanted me to think. This was purposeful. They wanted me to think that enthalpy changes the activation energy, or just misread the activation energy as enthalpy because you're in an exam, you're stressed. And that's exactly what I did. And so I made some fake numbers that calculated K with -1 and +1 for the EA. And then I was checking my work. I actually only saw I got it wrong after. I didn't even catch it when I was checking my work. It was whenever I was grading myself. And I was like, why did I get this wrong? Oh my god, that's not right. Okay. So there's nothing in the Arrhenius equation that changes with endothermic or exothermic. The activation energy is always going to be positive. Okay. So it's always going to be positive. So that does not change literally anything. Okay. So both B and D are incorrect. So it's either going to be A or C. This is one that's also in the subject guide, but either way, if you forget where it should be increases, but if you forget, I'm going to tell you my trick. Fake numbers. You should make up some numbers. I'm not kidding. Okay, it's just make up some numbers and keep them all the same except for the temperature. Okay, so here's what I did. So I went K is going to be equal to 1 e to the negative 1, 8.31 times 1. Okay, and then I did the same thing with K is going to be equal to 1 e negative 1, 8.31 times 2, a higher temperature, just to see how the K changed. Okay, and I actually don't have my calculator because I actually don't know the answer to this, so we're going to just do this real quick. E raised negative 1, 8.31 times 1. Boom. So that is 0.89 for that first one, that first temperature. And then if you change that to 2, is it then becomes 0.94. So it increases. As temperature increases, the K also increases. Okay, so that is why it is A. Fake numbers come in clutch a lot of the times when you can't know if you remembered something. Never underestimate. I don't think I've never seen anybody else use this technique actually. And I explain it to students and they're baffled. They're like, but where'd you get those numbers? My brain. As long as they don't matter, it doesn't matter. Just use some fake numbers. As long as if you're just testing the relationship between two things, just make some stuff up. Okay, and making it one is usually the easiest to keep it all the same. So there's that. Normally, with a lot of equations, you can just see if it's on the same side of the equation. They're inversely related. Opposite sides, they're positively related. However, with the exponent, like the e raised to, I don't know how that applies there. So I didn't want to get into that. So fake numbers it is. So that 28 is A, and you should always use fake numbers. It's such a good technique. Number 29, it's time to go. And so this one is the system at equilibrium. You have this sulfur dioxide and oxygen forming sulfur trioxide. Oh my god, that's like a acid rain type equation. Anyways, and our K is 4.3. And it tells us what is the value of the equilibrium constant for the reverse reaction. This one's just memorization. So the reverse reaction is always the reciprocal. So it's just 1 over 4.3. That's it. So that one is C. I don't really know how else to explain that one. Um, where B is wrong because it's not the same. It's the reverse reaction. That would be weird. Square root would be if you were dividing by 2. Like if it were still the forward reaction, but everything was like divided by 2. So that wouldn't be right. And then A would be the square root of 1 over 4.3. So that'd be like if you reversed it and then divide everything by 2. So that's also not right. So let's see. Just kidding. Actually, I thought about it for more than 0.5 seconds. There is actually reasoning, but I've never genuinely thought of this, and I feel bad now. I should have thought of this at some point in time and explained this to students. Students hopefully got it, but I didn't. But either way, equilibrium constant is in general. Oh, that's my eraser. K is always just the product's concentration over the reactant's concentration. So in your forward, you have your reactants going to your products. In your reverse reaction, your products now become reactants, reactants now become products. So these switch. So that's why it's the reciprocal of the equilibrium constant whenever you reverse the equation. That's it. That's why. Same reason with also why, rather than multiplying it by 1/2, whenever you divide everything by 2, why instead you make it to an exponent of 1/2 because everything is like your concentrations of products and reactants are to their stoichiometric coefficients. So that's also why. Whoa, crazy. Okay, this is one where question number 30. What is the effect of doubling the pressure on the equilibrium? All other conditions remain unchanged. You may notice, I think it's really funny. I didn't notice this until a student pointed out. Like, oh, pressure. Whenever we say anything about pressure, do we think about volume? And so that's why a lot of times when they say things about pressure, they say all other things remain unchanged because otherwise students start overthinking it. Anyways, so it's the effect on the equilibrium position and the equilibrium constant. First thing we're going to handle is the easier one, is the equilibrium constant. Okay, is the only thing that is affecting that is going to be temperature. And since pressure is not temperature, it's going to remain unchanged. No change, no change, blank, blank. So that puts C and D out of the running. Okay. HL, it's nice because I can actually explain the change in temperature thing. Is because whenever the like equilibrium constant, the equations that we know with it, so the one that we do know is the change in Gibbs free energy is equal to negative RT ln K. T is the only equation. I mean, T is the only thing that's in there. Temperature, pressure, concentration, blah, 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 blah. None of that is in there. It's only temperature. So that's the only one that has an effect on the equilibrium constant. Now, the effect of the equilibrium position, different. So this is where going to be comparing the moles of gas. Whenever you are doubling the pressure, you are increasing the pressure, obviously. And so whenever you do that, the system is going to shift in whichever direction has less moles of gas. So it's going to be trying to undo that increase. Is the system's like, I increased the pressure, and then some guy in the back's like, no, you didn't, and fixes it, you know? So Uno reversed. I always like to do the Uno reverse card to explain Le Chatelier's principle. So on our reactant side, you have 3 moles of gas versus on our product side, you have might have the batteries low. Anyways, 2 moles of gas. And so the side that has less, because we're undoing the increase, so we're decreasing less moles of gas, less pressure, is our products. So it is going to shift to the right. So shift right, boom, right, boom. So that one is going to be A for that number 30.